A fighter jet engine is one of the most complex machines ever created. A true engineering marvel. A fighter jet has 5 main parts: air intake, compressor, combustion chamber, turbine, and exhaust nozzle. It works on Newton's third law of motion. For every action, there is an equal and opposite reaction.
Almost 25 years in the Swedish Air Force, flying all kinds of airplanes, different roles. I remember that day very clearly when I first sat in a Gripen Charlie Delta version. If we then look at Gripen EF, it's 20 years of technological evolution.
Welcome back to our channel. Today, we're stepping inside the world of one of the most powerful machines ever built, the F-135 fighter jet engine. This beast pushes out over 40,000 pounds of thrust. That's raw power you can actually feel. Imagine standing next to something with over 50,000 horsepower. It's not just engineering, it's controlled force. And right now, we're standing inside a facility where this kind of power is tested. Look around. This is a test cell, basically a building inside another building, designed to handle extreme noise, heat, and pressure. Every edge, every blade inside this engine is razor sharp and built with insane precision. One small mistake here, and everything changes. But here's where things get really interesting. For decades, advanced fighter engines like the F-135 kept allies dependent on the United States. If you bought the aircraft, you were locked into their supply chain, their upgrades, and their rules. That's how control was maintained. Now, that model is starting to shift. In Montreal, a new chapter is beginning. Rolls-Royce is moving towards 6th-generation engine production. And this isn't just about technology, it's about sovereignty. Countries like Canada are stepping into a future where they can build, maintain, and control their own fighter engine power. We're talking about next-gen engines with adaptive cycle technology, engines that can switch modes mid-flight for power or efficiency. Advanced ceramic materials that can survive temperatures above 2,000 degrees Celsius, and onboard electrical power in the megawatt range, enough to support future weapons and systems we're only beginning to see. This isn't just an upgrade. This is a complete shift in who controls air power. And the foundation for all of this? It's already here. Canada's aerospace industry, built on decades of experience like the PT6 engine program, with over 50,000 units produced, proves they have the skill, the workforce, and the supply chain to make this real. This isn't theory anymore. It's happening. So what we're witnessing right now is more than just a new engine. It's the beginning of a future where allies don't just fly advanced fighters, they build their power from the ground up. Before we go deeper, take a second to like the video and subscribe. More than 98% of viewers watch without subscribing, and your support helps us keep bringing you powerful stories like this. This isn't just one factory, it's an entire ecosystem. In Quebec, you've got a massive aerospace network, companies like Bombardier, CAE, and hundreds of highly specialized suppliers. These are the people who design, build, and perfect some of the most advanced machines in the world. And now, all of that experience is being used to build next-generation fighter engines. We're talking about a production facility covering over 100,000 square meters. Inside, it's not your typical factory. It's more like a high-tech laboratory. Clean room environments where even microscopic dust particles are controlled. Because when you're building turbine blades, even a tiny imperfection can affect airflow and performance. Temperature and humidity are tightly controlled. Why? Because metal expands and contracts, and when you're working at extreme precision, even small changes can ruin alignment. Then comes testing. These engines are pushed to their absolute limits inside special test cells, fully isolated so they can run at full power without shaking the entire city. And that's just the beginning. At the Mirabel Testing Center, engineers simulate real flight conditions, from sea level all the way up to 60,000 feet, freezing cold to extreme heat. Every scenario a fighter jet could face, tested right here on the ground. They also run vibration tests to simulate intense combat maneuvers, and endurance tests that push engines through thousands of hours of operation just to make sure nothing fails when it matters most. Because in this world, failure is not an option. Now here's the smart part. Instead of building everything from scratch, this program is using Canada's existing aerospace strength, especially the PT6 engine legacy. Over 50,000 engines produced. That means the tools, the workforce, and the expertise are already there. So instead of wasting billions on new facilities, they're upgrading what already works. Faster, smarter, and more efficient. And all of this is leading to something even bigger. A sixth-generation engine developed by the UK, Italy, and Japan under the GCAP program. This engine is designed to go beyond anything we have today. We're talking about up to 190 kilonewtons of thrust with afterburner, enough power to push fighters into sustained supersonic flight without constantly burning fuel. And the real game changer? Adaptive cycle technology. This engine can actually change how it operates during flight. Need maximum power for combat? It shifts into high thrust mode. Cruising long distances? It switches to fuel-efficient mode automatically. One engine, multiple personalities. That means better performance, longer range, and more flexibility in real combat situations. This is not just evolution. This is a complete rethinking of how fighter engines work, built on precision, tested to extremes, and powered by a global alliance that's reshaping the future of air power. In next-generation engines, everything happens automatically. As the pilot moves the throttle, the engine instantly adjusts itself, changing airflow, nozzle shape, and internal pathways in real time. No manual control needed. The system is so smart, it handles all the complexity in the background, giving the pilot pure performance without extra workload. But here's the real game changer: thrust vectoring. This engine doesn't just push the aircraft forward, it can actually redirect its thrust in different directions. That means even when the jet is flying at extreme angles, where wings and control surfaces start to lose effectiveness, the engine still keeps the aircraft fully under control. In simple words, the jet can pull off moves that normal aircraft just can't. This gives pilots a massive advantage in close combat. Faster turns, sharper angles, and control even in situations where physics would normally say game over. And it doesn't stop there. Inside the engine, new materials called ceramic matrix composites are being used. These can handle temperatures above 2,000 degrees Celsius, way hotter than traditional metals. Higher temperature means better efficiency, and that means more power from the same fuel. In fact, this technology can improve fuel efficiency by around 15%. That's huge. It means longer range or the ability to carry more weapons instead of extra fuel, more flexibility, more mission power. Now, let's talk about something even more futuristic. These engines don't just produce thrust, they generate massive electrical power. We're talking megawatt-level energy. Why does that matter?
Because future fighter jets will rely on systems like advanced radar, electronic warfare, and even laser weapons. All of that needs serious power, and this engine becomes the source. Without it, aircraft would have to carry extra equipment, adding weight and reducing performance. But with this engine, everything is built in. Now here's where it gets really interesting for the future. There's a real possibility that aircraft like the Gripen could one day upgrade to this new engine. Right now, it uses an engine producing around 98 kilonewtons of thrust. This next-gen engine? Around 150 kilonewtons. That's over 50% more power. Think out what that means. Faster acceleration, higher climb rate, better turning performance, more payload. And the best part? You don't need to redesign the entire aircraft. With some upgrades like stronger engine mounts, better air intakes, and improved cooling, the same airframe could unlock a completely new level of performance. So what we're looking at here is not just a better engine, it's a transformation. An engine that adapts, controls, powers, and evolves, turning already capable fighters into something far more powerful. And this is what the future of air combat looks like.
Building a brand new fighter jet can take over 10 years, but upgrading an existing aircraft with a next-generation engine, that could take just 3 to 5 years from decision to full operational use. Think about that. Instead of waiting a decade, you can boost your air power in just a few years. And the results are massive. With a next-gen engine swap, aircraft performance jumps to a whole new level. Top speed could push beyond Mach 1.8, compared to around Mach 1.6 today. That extra thrust helps the jet break through drag and fly faster than ever. Altitude? Even higher. With more power, jets can climb beyond 60,000 feet, giving them a major advantage, flying above enemy threats, launching weapons from safer distances, and staying harder to detect or intercept. And then comes range. Thanks to adaptive cycle technology, the engine uses fuel more efficiently. That means the same fuel load can take the aircraft further, or pilots can carry more weapons instead of extra fuel tanks. More reach, more firepower, more flexibility. But this isn't just about performance. This is about control. In traditional setups, countries depend heavily on foreign manufacturers. If you need upgrades, spare parts, or changes, you have to wait. And sometimes those decisions are driven by politics, not urgency. That's where this new model breaks the system. Through partnerships like Rolls-Royce in Montreal, Canada isn't just buying engines, it's gaining full access to the technology. That means engineers can understand, modify, and improve the engine themselves.
No waiting, no restrictions. If something needs fixing or upgrading, they can do it on their own timeline. And this is huge, because for decades, advanced fighter engines in North America came almost entirely from U.S. companies like Pratt & Whitney and General Electric. That created a single point of dependency. If relations change or priorities shift, operational capability could be affected. Now, that dependency is starting to break. A new European-based supply chain is emerging, one that isn't controlled by U.S. export rules. That gives countries like Canada the freedom to build, maintain, and operate their air power based on their own national interests. And it goes even deeper. This isn't just assembly work. Canadian engineers and industries are directly involved, building critical components like turbine discs, combustion systems, compressor blades, and fuel injectors. This is real manufacturing, real expertise, built on decades of experience from programs like the PT-6 engine. So what we're seeing here is more than an upgrade. It's a shift from dependency to independence, from waiting to acting, from buying power to building it. And in today's world, that kind of control might be the most powerful advantage of all.
Inside these facilities, everything is built with extreme precision. We're talking about advanced 5-axis CNC machines shaping complex parts from solid metal, and processes like hot isostatic pressing that make components stronger and denser under high pressure and heat. Every single part is measured down to the micron level using laser-based systems. And before anything is approved, it goes through non-destructive testing, meaning engineers can check for hidden flaws without damaging the part. This isn't new for Canada. These capabilities already exist thanks to decades of commercial aerospace experience. Now they're being pushed into military-grade production. And it starts small, but grows fast. In the first phase, Montreal could produce around 10 to 20% of engine components, building expertise and validating quality. But in the next phase, that scales up to 50 to 100 complete engines every year, not just for Canada, but for export. And that's where things get big. This kind of production could create 5,000 to 10,000 direct jobs, plus 20,000 to 30,000 more across suppliers, tooling, and support industries. Entire regions benefit. The economy grows. The industrial base gets stronger. But the real shift is strategic. Right now, engines like the F-135 are fully controlled by U.S. companies. Countries using them depend on American approval for maintenance, upgrades, and even operational decisions. That's a serious limitation. With this new system, engines built in Montreal, powered by partnerships like Rolls-Royce, change that completely. Countries gain control over their own aircraft, their own upgrades, and their own missions. No external approvals, no delays. And that removes a major concern many critics talk about, the idea that advanced systems could be restricted or limited by foreign control. Here, that risk disappears. Now imagine the global impact. Canada could supply engines and aircraft to countries that need reliable, independent defense solutions, like Ukraine, Poland, or others looking to move away from older systems or reduce dependency. And here's the key advantage. With a fully independent supply chain, Canada and its partners can support these aircraft for their entire life cycle, from manufacturing to maintenance to upgrades, without relying on outside approval. That means faster decisions, stronger partnerships, and true operational freedom. And there's one more powerful benefit, especially for extreme environments. In places like the Arctic, conditions can swing from -40 degrees on the ground to over 2,000 degrees inside the engine. That kind of stress destroys traditional materials over time. But with advanced ceramics and new materials, these engines are built to survive that extreme cycle, again and again, without losing strength. So what we're looking at here is not just advanced engineering. It's a complete system, built for precision, scaled for production, designed for independence, and ready for the most extreme conditions on Earth. And that's exactly what the future of air power demands.
In places like the Arctic, temperatures can drop below -30 degrees Celsius. For many engines, that's a nightmare. Starting becomes unreliable, systems freeze, and response time suffers. But next-generation engines are built differently. With advanced fuel systems and ignition technology, these engines can start reliably even in extreme cold. That means when a threat appears, like unidentified aircraft approaching airspace, jets can be in the air within minutes, not delayed by engine issues. And in defense, those minutes matter. Now let's move to something even more powerful: maintenance independence. With full access to the technology, Canada doesn't have to wait for outside support. If something goes wrong, engineers can diagnose it, fix it, and even manufacture replacement parts locally. No delays, no dependency. And it goes further. At facilities like Mirabel, Canada can test and certify its own upgrades and repairs. That means no waiting for foreign approval. Everything can be validated in-house, on their own timeline. That's true sovereignty. But this isn't just about Canada. This model proves something bigger, that middle power nations can build advanced aerospace industries. For decades, only a few countries controlled this level of technology. Now, that barrier is starting to break. Countries like Australia, or others with strong industrial bases, could follow the same path. And when that happens, the global defense landscape changes. But there's another hidden advantage: technology spillover. All the innovation from military engine development, advanced materials, precision manufacturing, testing methods, doesn't stay in defense. It flows into commercial aerospace. Companies can build better business jets, more efficient aircraft, and gain a competitive edge globally. And behind all of this is people. This program creates a new generation of engineers and specialists, experts in engine design, material science, and advanced manufacturing. And instead of losing that talent to other countries, it stays local. It grows. It strengthens the industry. So when you step back and look at the full picture, this isn't just about a new engine. It's about breaking long-standing dependencies. It's about shifting from relying on others to building your own future. It's about control, capability, and confidence. And if this momentum continues, we could be looking at a world where advanced air power is no longer controlled by just a few nations, but shared by those willing to invest, innovate, and lead. If you found this deep dive valuable, hit the like button and subscribe to the channel. The next few years will be critical, and we'll be here to break it all down for you. Thanks for watching, and we'll see you in the next one.